Now, in this lecture, we'll find out the area of the green shape. In the drawing, we have a circle. Inside this quarter circle, we know that the radius of this small circle is equal to the square root of 2 units in its length. And our mission is to find out the area of this green shape. Okay, so first of all, we define the relevant points to this question with letters. We define this point as A. We define this point as B. This point is the center of the quarter circle. We define the center of the quarter circle as O. We define this point as C. We define this point as D. This point is the touching point between this small circle and the big quarter circle. We define the touching point as E. And finally, we define the center of this small circle, this point, as F. In the next step, we join points F and C together by a straight line. What is the definition of line segment FC? Line segment FC starts from point F, that is the center of the small circle, and ends at point C, that is the point of the small circle itself. This is exactly the definition of a radius. So FC is the radius of the small circle that is equal to the square root of 2 units according to what is given as the question. Here we'll implement rule 1. A bit quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. In the drawing, we have a circle, and we have, this is tangent AB, that is tangent to this circle at point M. Point M is the point of tendency of tangent AB with this circle. And we have the radius OM is equal to capital R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 1. So we can implement rule 1 in our drawing. Why? Because in our drawing we have the radius FC of this small circle that is drawn to point C, that is the point of tendency of tangent OD with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OD will be perpendicular to the radius FCF. So if OD is perpendicular to CF, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we have the radius FB of the small circle that is drawn to point B, that is the point of tendency of tangent AO with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius BF. So if AO is perpendicular to BF, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So in this small quadrilateral FBOC, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus this fourth angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle here must be equal to 90 degrees in its size. Again, in order to complete the sum of the angles inside the small quadrilateral FBOC to 360 degrees, the missing angle here must be equal to 90 degrees in its size. So, inside the small quadrilateral BFOC we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So, we will relate to this quadrilateral BFOC with 4 right angles as a rectangle. And we also note that the opposite sides of a rectangle are equal to each other. That is to say, side BF equals to the opposite side OC in rectangle BFOC. But BF equals to the square root of 2, therefore OC must be also equal to the square root of 2 units in its length. Likewise, according to the same rule, in rectangle BFOC, side FC must be equal to the opposite side BO. But FC equals to the square root of 2 units, therefore BO must be also equal to the square root of 2 units in its length. In the next step, we join points F and O together by a straight line. By joining points F and O, we created the right triangle OBF. The right triangle is also an isosceles triangle. Why? Because side BO equals to side BF. Those two sides are both equal to the square root of 2 units, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides in the right triangle BOF, those two angles must be also equal to each other. So if we define the size of this angle as alpha, then this angle must be also equal to alpha because they are equal to each other. And we also note that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have in the right triangle BOF? We have alpha plus alpha, that is 2 alpha, and this angle equals to 90 degrees. So in total, in the right triangle BOF, we have the angles of 2 alpha plus the right angle is equal to 90 degrees. In total, the sum of those three angles must be equal to 180 degrees according to the rule that I mentioned. Here, we subtract 90 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 90 degrees. It is 90 degrees. So here, we divide this equation by 2, and finally, we will get that the missing angle alpha equals to 90 degrees over 2, that is 45 degrees. So actually this is angle alpha that is equals to 45 degrees in its size. And this is also angle alpha that is equals to 45 degrees. Okay, so here we'll continue to focus on the right triangle BOF, and we'll implement the Pythagoras theorem in this right triangle BOF. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So, actually, in the right triangle BOF, the hypotenuse is OF, and therefore the square of the hypotenuse is OF squared, and it must be equal to BF squared plus BO squared. Repeat again, according for the Pythagoras theorem, in the right triangle BOF, OF square must be equal to BF square plus BO square. So OF square, that is the square of the hypotenuse, must be equal to BF square. BF is square root of 2, therefore BF square is square root of 2 square, that is 2, plus BO square. BO is also square root of 2, therefore BO square is square root of 2 square, that is 2. So in conclusion, we found out that OF square equals to 2 plus 2, that is 4. Here we take a root out of this equation, and finally we get that OF equals to the square root of 4, that is 2. So OF equals to 2 units in its length. OF equals to 2 units. This is done in the drawing. OF equals to 2 units in its length. So in the next step, I will present to you a new rule and we will implement the new rule in our drawing. The new rule is rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together must pass through their touching point. So in the drawing we have two circles. This small circle is located inside the big circle, and those two circles touch each other internally at point P. So actually we have here an internal match between those two circles. That is to say, they are touching each other internally at point P. And according to this rule 9, whenever you have two circles with an internal match between them, that is to say, when they are touching each other internally, then the straight line that connects their centers together must pass through their touching point. The center of the big circle is here at point O. The center of this small circle is here at point M. And the straight line that connects their centers together is the straight line OM. And according to this rule 9, the straight line OM must pass through point P, that is their touching point. Again, the straight line OM must pass through point P, that is their touching point. OMP is one straight line. OMP is one straight line. So we can actually implement rule 9 in our drawing. Why? Because in our drawing, first of all, this small circle is located inside the big quarter circle, and they touch each other internally at point E. Therefore, we have here an internal match between those two circles. For that reason, we can implement here rule 9. The straight line of the big quarter circle, that is also the straight line of the big circle, is here at point O. The straight line of this small circle is here at point F, and the straight line that connects their centers together is the straight line OF. And again, the center of the big quarter circle is here at point O, the center of this small circle is here at point F, and the straight line that connects their centers together is the straight line OF. And according to rule 9, the straight line OF must pass through point E. Again, the straight line OF must pass through point P. Or OFE is one straight line. Again, OFE is one straight line. So, we'll extend the straight line OF, and according to rule 9, the straight line OF must pass through point E. Okay, again, here, OFE is one straight line. So I write it down here. Line segment OFE is one straight line. But what is the other definition of line segment OFE, or of the straight line OFE? The straight line OFE starts from here at point O, that is the center of the big quarter circle and the big circle, and ends at point E, that is the point on the big circle itself. This is exactly the definition of a radius. So OFE is the radius of the big circle. So we define the radius of the big circle is capital R. So I write it here. Capital R is the radius of the big circle. And according to what we just found out, that capital R, the radius of the big circle capital R equals to OFE. What is the definition of line segment FE? Line segment FE starts from point F, that is the center of this small circle, and ends at point E, that is a point on the small circle itself. This is exactly the definition of a radius. So FE is the radius of this small circle that is equals to the square root of 2 units in its length according to what is given as the question. From the drawing, it is very easy to see that the length of line segment OFE is OF plus FE. OF equals to OF plus FE. Why? Because OFE, because of the fact that OFE is one straight line, then the length of line segment OFE must be equal to OF plus FE. OF is 2 and FE is square root of 2. So from this equation we derive that capital R equals to 2 plus square root of 2. Capital R, that is the radius of the big circle, equals to 2 plus square root of 2 units in its length. We define the intersection point between the radius OFE and this small circle here. This point is the intersection point. We define this point as H. Edge FE is part of line segment OFE. And because of the fact that edge FE is part of OFE, it means that, and we know that OFE is one straight line, therefore edge FE is also one straight line because it is part of OFE. So edge FE is a straight line that touches this small circle at points H and E. Any straight line that touches the circle at 2 points must be a chord. So edge FE is the chord of this small circle, and it is a special chord that passes for point F. For point F, that is the center of this small circle. And we know that any chord that passes for the center of a circle must be the diameter of the circle. So edge FE, line segment edge FE, is the diameter of the small circle. Why? Because it passes for point F, that is the center of the small circle. And F is the diameter of the small circle. And we also know that the diameter of any circle bisects the circle into 2 halves. So edge FE bisects this circle into 2 halves. This is the first half and this is the second half. So the first half of a circle is defined as a semicircle. So therefore this shape is a semicircle. We can say it is a small semicircle of the small circle. Okay, so it is a small semicircle of the small circle. It is half of the small circle, therefore it is a small semicircle of the small circle. Okay? The next step, I will present to you a new notion that is actually a sector. Okay? So, what is a sector? A sector is part of a circle in the drawing. We have a circle and the orange shape and the green shape here A or B. This green shape A or B is a sector that's actually part of this circle. We can, if we see the circle, if we look at this circle, it's a cake, then the green shape A or B is one slice of a cake. Okay? So we can see a sector is one slice of a cake. If we look at the circle, it's a cake. And the green sector A or B consists of two legs. The first leg is AO and the second leg is BO. Both those two legs are the radii of this circle that is equal to R, and the angle between the legs of this sector A or B is angle theta. Okay? And the area of this green sector A or B is equals to the area of the circle, that is pi r squared, times theta, that is the angle between the legs of the sector, over 360 degrees. Again, conclusion, we can say that the area of a sector equals to the area of the circle that contains the sector times the angle between the legs of the sector over 360 degrees. Okay. Our mission is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of this green shape equals to the area of the big sector AOE, this big sector AOE. Here, this rounded line around AOE is the sign of a sector. It means sector AOE. Okay? This expression means sector AOE. And here the squared brackets is the sign for the area. So this expression in total, it means that the area of sector AOE, the area of the big sector AOE. So the area of this green shape equals to the area of the big sector AOE minus the area of the small semicircle. Minus the area of this shape B edge O, minus the area of shape B edge O. So minus the orange shape B edge O. Repeat again, the area of this green shape, in total, it is equals to the area of the big sector AOE. Again, the big sector is part of the big circle, minus the area of this small circle. The small circle is part, minus the area of the small semicircle. that is part of the small circle, that is half of the small circle, minus the area of this orange shape, HBO. Repeat again, the area of the green shape equals to the area of the big sector AOE minus the area of the small semicircle minus the area of the orange shape BHO. So first of all, we find out the area of the big sector AOE. What is the area of the big sector AOE? Repeat again that the area of the big sector AOE is part of the big circle. Therefore, the area of the big sector AOE equals to the area of the big circle, that is pi times capital R square times the angle between the legs of this sector. This is the AO is one leg and OE is the other leg, and the angle between the two legs is this angle, and we will find out that the size of this angle is 45 degrees. So it is 45 degrees over 360 degrees. So the area of the big sector in total equals to pi times capital R square times 45 degrees over 360 degrees. So it is pi times capital R square. We have already found out that capital R equals to 2 plus square root of 2. Therefore capital R square equals to 2 plus square root of 2 squared. And we have to multiply it by 45 degrees over 360 degrees. 45 degrees over 360 degrees, it is 1 over 8, so we divide it by 8. So the area of the big sector equals to this expression, that is pi times 2 plus square root of 2 square over 8. So it is pi and 2 plus square root of 2 square, according to the algebraic identity that a plus b square equals to a square plus b square plus 2 times ab, we get that 2 plus square root of 2 square equals to 2 square, that is 4, plus square root of 2 square, that is 2, plus 2 times square root of 2 divided by 8. So it is equals to pi, and inside the brackets we have 4 plus 2, that is 6, plus 2 times 2 is 4, so in total this expression equals to 4 times square root of 2 divided by 8. Here we divide both the numerator and the denominator of this expression by 2, and we get that the area of the big sector AOE, it will be equal to pi, inside the brackets we have 6, 6 over 2 is 3, plus 4 times square root of 2 over 2 is 2 times square root of 2, and we have to divide also the denominator 8 by 2. 8 over 2 is 4. So in conclusion, we found out that the area of the big sector AOE it is equals to pi times 3 plus 2 times square root of 2 over 4 square units. The area of the big sector AOE equals to pi times 3 plus 2 times square root of 2 over 4 square units. In the next step, we find out the area of the small semicircle. What is the area of the small semicircle? The area of the small semicircle equals to the area of the small circle, that is pi r square, over 2. So it is pi, and we know that r equals to the square root of 2, therefore r squared is square root of 2 squared, that is 2 over 2. 2 over 2 is 1, so we left only with pi. In conclusion, we found out that the area of the small semicircle is equals to pi square units. And finally, we have to find out also the area of this orange shape BHO. What is the area of the orange shape BHO? From the drawing, it is very easy to see that the area of this orange shape BHO equals to the area of the right triangle BFO minus the area of this small sector BHF. This small sector BHF. The small sector is part of the small circle, of course. So, in conclusion, we found out that the area of the orange shape BHO equals to the area of the right triangle BFO minus the area of the small sector BHF. So what is the area of the right triangle BFO? Side BF equals to side BO, so the height is equals to the base. So we know that the area of any triangle equals to the base of the triangle times the height to the base over 2. Here the base equals to the height, they are both equal to the square root of 2 units. So the base is square root of 2 times the height, that is also square root of 2, divided by 2. Square root of 2 times square root of 2 is 2, and 2 over 2 is 1. So in conclusion, we found out that the area of the right triangle BFO, in total, it is equals to 1 square unit. Now we have to subtract from the area of the right triangle BFO the area of the small sector BHF. What is the area of the small sector BHF? We know that the area of any sector equals to the area of the circle that contains the sector. The small circle contains the small sector, and we know that the area of the small circle equals to pi r squared times, so it is pi r squared times the angle between the legs of this sector BHF. This is the angle between the legs of this sector BFH. This angle equals to 45 degrees. So it is 45 degrees over 360 degrees. So in total, the area of the small sector BHF equals to pi r squared times 45 degrees over 360 degrees. So it is pi, and r is square root of 2, therefore r squared is square root of 2 squared, that is 2, multiplied by 45 degrees over 360 degrees. 45 degrees over 360 degrees, 45 degrees over 360 degrees, it is 1 over 8, so we have to divide 2 pi by 8. Here we divide both the numerator and the denominator of this expression by 2, and we get that 2 pi over 2 is pi, and 8 over 2 is 4. So in conclusion, we found out that the area of the small sector BHF is equals to pi over 4 square units, and the area of the orange shape BHF is equal to the area of the right triangle BFO, that is 1, minus the area of the small sector BHF, that is pi over 4. In conclusion, we found out that the area of the orange shape BHF is equals to 1 minus pi over 4 square units. Our mission is to find out the area of this green shape. And we now repeat again that the area of the green shape in total it is equals to the area of the big sector AOE. We have already found it, minus the area of the small semicircle, we have already found it, minus the area of the orange shape BHO, we also found it, again the area of the green shape equals to the area of the big sector AOE minus the area of the small semicircle minus the area of the orange shape BHO. So the area of the green shape equals to the area of the big sector AOE. We have already found out the area of the big that the area of the big sector AOE equals to pi times 3 plus 2 times square root of 2 over 4 square units minus the area of the small semicircle. We have already found out that the area of the small semicircle equals to pi square units minus the area of the orange shape. We have already found out that the area of the orange shape equals to 1 minus pi over 4 square units. So the area of the green shape equals to the value of this expression. So we just simplify this expression in order to find out what is the area of the green shape in terms of numbers. So we have here, we'll open the brackets here, pi times 3 is 3 pi, plus 2 times square root of 2 times pi, over 4. We have here minus pi, and we have here minus before the brackets. So we'll open the brackets here. After we open the brackets, we'll get here minus 1, and we have here minus times minus is plus. So it is minus 1 plus pi over 4 in total. So the area of the green shape will be equal to 3 pi plus 2 times square root of 2 times pi over 4, and we have here minus pi plus pi over 4 is minus 3 quarters pi, and we have here minus 1. So we'll multiply minus 1 by 4, and then we'll divide it by 4 in order to have a common factor with the other two expressions. So minus 1 times 4 is minus 4 divided by 4. So those three expressions have the common factor of 4 in the denominator. So we write it again with 4 in the denominator. So, and we get that the area of the green shape in total will be equal to 3 pi plus 2 times square root of 2 pi minus 3 pi minus 4 divided by 4. So here we have 3 pi minus 3 pi is 0, and after we cancel 3 pi, we left only with 2 times square root of 2 times pi minus 4 over 4. Here we divide both the numerator and the denominator of this expression by 2, and we'll get that 2 times square root of 2 pi over 2 is square root of 2. Here we have actually we have here 2 times square root of 2 times pi, so 2 times square root of 2 times pi over 2 is square root of 2 times pi, and we have minus 4 over 2 is minus 2, and we have to divide the denominator of 4 also by 2. 4 over 2 is 2. So here we have 2 times square root of 2 times pi minus, so actually found out that the area of the green shape in total it is equal to either square root of 2 times pi minus 2 over 2. In terms of numbers, it is equal to 2.114 square units. Repeat again. The area of this green shape it is equal to either square root of 2 times pi minus 2 over 2. And in terms of numbers, it is equal to 2.114 square units. So in the next step, we'll summarize the lecture. In this lecture, we found out the area of this green shape. In the drawing, we have a circle. Inside this quarter circle, we know that the radius r of this small circle equals to the square root of 2 units in its length. Our mission is to find out the area of this green shape. So first of all, we defined the relevant points to this question with letters. We defined this point as A, we defined this point as B. This point is the center of the quarter circle. We define the center of the quarter circle, this point as O. We define this point as C, we define this point as D. This point is the touching point between the small semicircle and the big quarter circle. We define the touching point as C, and finally we define the center of this small circle, this point as F. Then we join points F and C together by a straight line. Point F is the center of this small circle, and point C is the point on the small circle itself. Therefore, FC is the radius of this small circle that is equal to the square root of 2 units according to what is given as a question. We have the radius FC that is drawn to point C, that is the point of tendency or tangent OD with this small circle, and whenever you have a radius that is drawn to the point of tendency, then tangent OD will be perpendicular to the radius CF. If OD is perpendicular to CF, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius FB that is drawn to point B, that is the point of tendency or tangent AO with this small circle, and whenever you have a radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius BF. If AO is perpendicular to BF, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. So inside the small quadrangle BFOC, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus the size of this fourth angle. In total, the sum of those 4 angles must be equal to 360 degrees according to the rule. Then the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, the missing fourth angle here must be equal to 90 degrees in its size. So inside this small quadrangle BFOC, we have 4 right angles. And you know that any quadrangle that has 4 right angles must be at least a rectangle if not a square. So we relate to this quadrangle BFOC as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side BF equals to the opposite side OC. But BF equals to the square root of 2 units, therefore OC must be also equal to the square root of 2 units in its length. Likewise, according to the same rule, in the rectangle BFOC, side FC must be equal to side BO, but FC equals to the square root of 2, therefore BO must be also equal to the square root of 2 units in its length. So actually we found out that quadrangle BFOC is not a rectangle but a square because of the fact that all of its sides are equal to each other. Each side is equal to the square root of 2 units in its length. Then you join points F and O together by said line. By joining points F and O, we created the right triangle BFO. In the right triangle BFO, those two sides are both equal to the square root of 2 units, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be also equal to each other. So if we define this angle as alpha, then the other angle must be also equal to alpha because they are equal to each other. And we also know that the sum of the angles in the triangle is equal to 180 degrees. So which angles we have inside the right triangle BFC? We have alpha plus alpha that is to alpha plus this angle that is the right angle. In total, the sum of those two angles must be equal to 180 degrees. That is to say 2 alpha plus 90 degrees must be equal to 180 degrees. Here we subtracted 90 degrees from this equation and found out that 2 alpha equals to 180 degrees minus 90 degrees, it is 90 degrees. So 2 alpha equals to 90 degrees. Here we divided this equation by 2 and found out that the missing angle alpha equals to 45 degrees. So this angle alpha equals to 45 degrees, and this is also angle alpha that is equals to 45 degrees in its size. Then we implemented the Pythagoras theorem on the right triangle BF4. According to the Pythagoras theorem, in the right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle BF4 is OF, and so the square of the hypotenuse is OF squared, and it must be equal to OB squared plus BF squared. Repeat again. In the right triangle BOF, according to the Pythagoras theorem, OF squared equals to BF squared plus BO squared. So OF squared, that is the square of the hypotenuse, must be equal to BF squared. BF is square root of 2, therefore BF squared is square root of 2 squared, that is 2, plus BO squared. BO is also square root of 2, therefore BO squared is square root of 2 squared, that is 2. So in total we found out that OF squared equals to 2 plus 2, that is 4. So OF squared equals to 4. We took out of this equation and finally found out that OF equals to the square root of 4, that is 2. So here OF equals to 2 units in its length. Then I presented to you rule 9 and we implemented rule 9 in our drawing. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together must pass through their touching point. So in this moment we have an internal arch between those two circles. Why? Because of the fact that the small circle is located inside the big circle and they touch each other internally at point P. So whenever you have an internal notch between two circles, you can implement rule 9. The center of the big circle is here at point O. The center of this small circle is here at point M. And the third line that connects the centers together is the third line OM. And according to this rule 9, the third line OM must pass for point P. That is their touching point. Or OMP is one third line. Okay, OMP is one third line. We can actually implement rule 9 in our drawing. Why? Because of the fact that this small circle is located inside the big quarter circle and they touch each other internally at point E, therefore we can implement here rule 9. The center of the big quarter circle is here at point O. That is also the center of the big circle. The center of this small circle is here at point F. And the third line that connects the centers together is the third line OF. And according to this rule 9, the third line OF must pass through the touching point, it's actually point E, or OFE is one third line. Again, according to rule 9, OFE is one third line. So OFE is a straight line. So what is the other definition of the straight line OFE? Because line segment OFE starts from point O, that is the center of the big circle, and ends at point E, that is the point of the big circle itself. This is exactly the definition of a radius. So OFE is also the radius of the big circle. We define the radius of the big circle as capital R. Here capital R is the radius of the big circle. And capital R equals of course to OFE. But what is the length of OFE? OFE equals to OF plus FE. Why? Because OFE is one straight line, therefore OFE equals to OF plus FE. What is the definition of line segment FE? Line segment FE starts from point F, that is the center of this small circle, and ends at point E, that is the point of the small circle itself. So this is exactly the definition of a radius. So FE is the radius of this small circle that is equals to the square root of 2. Again, OFE equals to OF plus FE. OF is 2 and FE is square root of 2. So in total, OF plus OFE equals to 2 plus square root of 2 units. So from this equation we derive that capital R equals to 2 plus square root of 2. That is to say, capital R, that is the radius of the big circle, equals to 2 plus square root of 2 units in its length. So we know that OFE is one straight line. We define the intersection point between the straight line OFE and this small circle as H. If OFE is one straight line, then HFE must be also a straight line because HFE is part of OFE. And the straight line HFE touches the small circle at point E and here at point H. Any straight line that touches the circle at 2 points must be a chord. So HFE is a chord of the small circle that passes through point F, that is the center of the small circle. And any chord that passes through the center of a circle must be the diameter. So in conclusion, found out that HFE is the diameter of the small circle. Here, HFE is the diameter of the small circle. And we know that the diameter of any circle bisects the circle into 2 halves. So the diameter HFE bisects this small circle into 2 halves. This is the first half, and this is the second half. So what is the definition of half of a circle? It is a semicircle. So in conclusion, we found out that this shape is a semicircle, or it is actually a small semicircle. It is half of the small circle, therefore it is a small semicircle. Then I presented to you the notion of a sector. What is a sector? A sector is part of a circle. This is a circle, and the green shape AOB is a sector. If we look at this circle as a cake, then AOB is one slice of this cake. So a sector is like a slice of a cake. So the green shape AOB is a sector. The sector consists of 2 legs. The first leg is AO and the second leg is BO. Both those two legs are defined as the radii of the circle, that is R. And the angle between the legs AO and BO of this great sector AOB is theta. And what is the area of this sector AOB? The area of sector AOB equals to the area of the circle that contains the sector, that's actually pi r squared, times the angle between the legs of this sector, that is theta, over 360 degrees. Repeat again. The area of any sector equals to the area of the circle that contains the sector times the angle between the legs of the sector over 360 degrees. Our mission is to find out the area of this green shape. What is the area of the green shape? The area of the green shape equals to the area of the big sector AOE minus the area of this small semicircle minus the area of this orange shape HBO. Repeat again. The area of the green shape equals to the area of the big sector AOE minus the area of the small semicircle minus the area of the orange shape BHO. So what is the area of the big sector AOE? The big sector AOE is part of the big circle, and we know that the area of any sector equals to the area of the circle that contains the sector. The big circle contains the sector, and the area of the big circle equals to pi times capital R squared times the angle between the legs of this big sector AOE, that is 45 degrees, over 360 degrees. We already found out that capital R equals to 2 plus square root of 2, therefore capital R squared is equals to 2 plus square root of 2 squared. So pi R squared is pi times 2 plus square root of 2 squared, and 45 degrees over 360 degrees, it is 1 over 8. So we have to divide the area of the big circle by 8. And so this expression equals to pi, and inside the brackets we have 2 plus square root of 2 squared is 2 squared, that is 4, plus square root of 2 squared, that is 2, plus 2 times square root of 2, plus 2 times square root of 2, all divided by 8. So 4 plus 2 is 6. We have pi inside the brackets, we have 4 plus 2 is 6, and 2 times 2 is 4, so in total this expression equals to 4 plus 4 times square root of 2 divided by 8. Here we divided both the numerator and the denominator of this expression by 2, and found out that we have here pi, and inside the brackets we have 6. 6 over 2 is 3, plus 4 times square root of 2 over 2 is 2 times square root of 2, and we have to divide the denominator 8 by 2, so 8 over 2 is 4. So in conclusion, we found out that the area of the big sector AOE is equals to pi, inside, pi times 3 plus 2 times square root of 2 over 4 square units. In the next step, we found out the area of this small semicircle. The area of any semicircle equals to the area of the circle over 2. The small circle, the small semicircle is part of the small circle, and know that the area of the small circle is pi r squared. When we divide the area of the small circle by 2, we get the area of the small semicircle. So in total, the area of the small semicircle equals to pi r squared over 2. So it is pi times r squared. R is square root of 2, therefore r squared is square root of 2 squared, that is 2, divided by 2. Here we have 2 over 2 is 1, so we left only with pi. So in conclusion, we found out that the area of the small semicircle, this small semicircle equals to pi square units, and we have to subtract from the area of the big sector AOE, we have to subtract the area of this orange shape BHO. What is the area of the orange shape BHO? The area of the orange shape BHO, from the drawing it is very easy to see that the area of the orange shape BHO equals to the area of the right triangle BFO minus the area of the small sector BFH. it again. The area of the orange shape BHO equals to the area of the right triangle BFO minus the area of the small sector BHF. So what is the area of the right triangle BFO? The area of any triangle equals to the base of the triangle times the height to the base over 2. The base equals to the square root of 2, the height also equals to the square root of 2 divided by 2. Square root of 2 times square root of 2 is 2 and 2 over 2 is 1. So in conclusion found out that the area of this right triangle BFO equals to 1 square units. Now we have to find out also here the area of the right triangle BFO is 1 square units. Now we have to find out also the area of this small sector BFH. The small sector is part of the small circle, so the area of any sector equals to the area of the circle that contains the sector. The small circle contains the small sector, and the area of the small circle equals to pi r squared times the angle between the legs of this small sector, that is 45 degrees over 360 degrees. So in conclusion found out that the area of the small sector BHF equals to pi r squared times 45 degrees over 360 degrees. So it is pi and r is square root of 2, therefore r squared is square root of 2 squared, that is 2. So in total the area of the small circle equals to 2 pi, and we have to multiply it by 45 degrees over 360 degrees. 45 degrees over 360 degrees, it is 1 over 8. So in conclusion found out that the area of the small sector BHF equals to 2 pi over 8. Here we divided both the numerator and the denominator of this expression by 2 and found out that 2 pi over 2 is pi and 8 over 2 is 4. So in conclusion found out that the area of the small sector BHF is pi over 4 square units. And in total the area of the orange shape equals to the area of the right triangle BF4, that is 1, minus the area of the small sector BHF, that is pi over 4. So in total the area of the orange shape the area of the orange shape BHO is equals to 1 minus pi over 4 square units. Our mission is to find out the area of this green shape. The area of this green shape equals to the area of the big sector AOE minus the area of this small semicircle minus the area of this orange shape BHO. Repeat again, the area of the green shape in total, it is equals to the area of the big sector AOE minus the area of the small semicircle minus the area of the orange shape BHO. We have already found out that the area of the big sector AOE is equals to pi times 3 plus 2 times root of 2 over 4 minus the area of the small semicircle, that is actually equals to pi square units minus the area of the orange shape BHO, that is equals to pi minus 4 pi equals to 1 minus pi over 4 square units. So actually this expression equals to the area of the green shape. We just have to simplify this expression in order to find the area of the green shape in terms of numbers. Here we open the brackets. We have here pi times 3 is 3 pi. And we have here pi times 2 times square root of 2 is 2 times square root of 2 times pi over 4. And we have here minus pi. And we have here minus before the brackets. We open the brackets here. So after we open the brackets, we left with minus 1, and we have minus times minus is plus. So it is in total minus 1 plus pi over 4. So here we have 3 pi plus 2 times root of 2 pi divided by 4, and minus pi plus pi over 4 is minus 3/4 pi. Here we multiplied minus 1 by 4 and then we divided by 4 in order to a common factor with the other two expressions that have 4 in the denominator. So we found out that all the the denominator of the three expressions, they have 4 in the denominator, so you can write 4 in the denominator of those three expressions, only 1 4, and we have here 3 pi plus 2 times square root of 2 pi minus 3 pi minus 4 over 4. In the denominator we have 4 here. 3 pi minus 3 pi is 0, and we have here, after we left 3 pi, we left only with 2 times square root of 2 pi minus 4 over 4. Here we divided both the numerator and the denominator of this expression by 2, and found out that 2 times square root of 2 pi over 2 is square root of 2 times pi, and minus 4 over 2 is minus 2, and we have to divide the denominator of 4 also by 2. 4 over 2 is 2. So in conclusion, we found out that the area of this green shape, it is equal to either square root of 2 times pi minus 2 over 2 square units, or in terms of numbers, the area of this green shape, it is equal to 2.114 square units. Okay, thank you very much.